Hello there and welcome. This video is on section 4.7, where we're going to be finding the absolute max min in word problems. So you may recall we found absolute max min before, and absolute max min just means the highest or lowest possible y value in the problem. And those always occur either at a critical point or at an endpoint. So we'll review that as we see some examples. These are word problems, so of course they come with all the additional difficulties that you have in word problems. So I just put some reminders, some tips here. Remember, the most important part of the problem is to understand what's going on. So read it very carefully 2 or 3 or 4 times, circle the important information, try to identify the question, maybe paraphrase it, maybe write it in some math language. You want to organize that information somehow, either in a picture or table or something like that. You should really clearly define what letters are being used, what variables are using. If you have an X in your problem, then you should know what X is standing for. And you should write that down so the reader knows what X is measuring as well. And then make sure we use calculus to write down the information and the question. We're going to simplify our equation so it only has 2 variables. Right now, we can only do max min when we have 2 variables, like a y and an x, like an input and an output. In third semester calculus or third year calculus, we can do max and mins for 3 variables, 4 variables, things like that. But in calculus 1, our first year calculus course, we only do maxes and mins for a 2 variable equation. So we will have some equations where there may be more than 2 variables. So we'll need to simplify them. That's the step right here. Make sure to simplify your question so it has only 2 variables in it. Absolute max, absolute min, we're going to find by finding the critical points and endpoints, and make sure we also answer the question, because it's always painful when you do all the work and then you lose points because you didn't actually answer the question. So answer the question, make sure the answer is reasonable, and that would be how we do absolute max min word problems. All right, let's do some examples. We'll start off some simpler examples, and we'll work our ways up to some more complicated examples. All right, so my first example here, example A, we're looking for a number. It says find the number that is between 1 and 100, such the sum of the number and its reciprocal is small as possible. So some things to make note of. We're trying to find something as small as possible. That would be an absolute minimum. As small as possible is the absolute smallest, absolute minimum. What are we trying to find the absolute smallest of? The sum of something, the sum of the number and its reciprocal. So if we want to find the absolute minimum sum, then we got to find an equation for the sum, find the derivative, and set it equal to 0. If you're trying to find the minimum profit, you need to find an equation for profit, find the derivative, set it equal to 0. If you're trying to find the maximum area, you need to find an equation for area, you need to differentiate it, set it equal to 0, right? So make sure you kind of keep in mind that if you're looking for the maximum or minimum of something, you need to find an equation for that thing, differentiate it. Okay, so we need we need an equation for the sum. Let's define some variables. So let's say S is equal to the sum. We need to find an equation for S. We have a number, so let's say X is equal to the number. And the sum is the sum of the number and the reciprocal. So let's say R is equal to the reciprocal. All right, so we want to find the minimum S. And we need an equation for S. If we're trying to find the minimum S, of course, we have to find the equation for S. It's just the sum of the number and its reciprocal. So the number is X, and its reciprocal is R. So that's an equation for the sum, right, involving the variables that we've defined here. Now, there's a couple other things we need, is that there are some restrictions on the number and on the reciprocal. The number is between 1 and 100. So the number is between 1 and 100. That means X cannot be smaller than 1, nor can it be larger than 100. So it can be between 1 and 100. The reciprocal, well, how do you find the reciprocal of a number? The reciprocal is 1 over, right? Oops, 1 over 100, 1 over X. The reciprocal of X So maybe I'll say reciprocal of x here since I forgot. The reciprocal of x is 1 over x. So if x is between 1 and 100, the reciprocal would be somewhere in that region as well, 1 over 1 to 1 over 100, right? So that's where your reciprocal is, depending on what your x value is. We're going to have this function in terms of x in a moment, so we only really need the restriction on x, which is x has to be between 1 and 100. All right, how do we get an equation with only two variables? You may have noticed that this equation for s right here, it has three variables. It has s, it has x, has r. So this is what I mean by you need to simplify your equation so that it only has two variables. But we know what r is. R is 1 over x. That's the reciprocal equation. So we're going to rewrite this equation as s is equal to x plus what r is. R is 1 over x. So that's my equation for the sum. That's what we're trying to minimize, the sum. And it only involves two variables, x and s. So s would be like my y variable, x is my x variable. That is an equation with two variables. And now we can finish the problem. We need to find the critical points. We need to find the endpoints. Well, the endpoints are right here, 1 to 100. It told us that x has to be between 1 and 100. So those are the endpoints. Here, these are endpoints. And what about the critical points? Well, critical points are when the derivative is equal to 0 or when the derivative is undefined. So let's go ahead and find some derivatives. So that would be ds dx. The derivative of x is 1. The derivative of 1 over x is minus 1 over x squared. If you don't remember that, remember that the derivative of 1 over x is the same as the derivative of x to the minus 1, which is negative 1 x to the minus 2, which is just negative 1 over x squared. Okay, so that's what my ds dx is, 1 minus 1 over x squared. I need to find out when this is equal to 0. And I also need to find out when it's undefined. Those are how I find my critical points. All right, well, I can solve this equation right here for when it's equal to 0. I'll just make this 1 over x squared is equal to 1, or x squared is equal to 1, or x is equal to plus or minus 1. And for when it's undefined when we divide by 0. So we divide by 0 when the bottom is equal to 0, when x squared is equal to 0. Right? If you have the 0 on the bottom, you divide by 0, which is not calculable. We call that undefined. So x squared equaling 0 means x is equal to 0. Take the square root of both sides. So we got three critical points: x equals 1, x equals negative 1, and x equals 0. Those are three critical points. CP, critical points right here and right here. So there's three things that we need to check that are critical points, and two things we need to check for endpoints. 1 is an endpoint, and 100 is an endpoint, right? So there are endpoints and there are critical points. So now we essentially make a list of all our critical points and endpoints, and the absolute minimum has to be at one of those locations. It's just not possible for it to be anywhere else. All right, so if you're noticing there's a problem with some of the critical points, I'll discuss that in a moment. So nicely observed. So I get some x values, and I'm going to look at the value of the function itself, because absolute min, absolute max have to do with the highest y value and the lowest y value. In this case, we're looking for the lowest y value. That's a y value. That's not a derivative value. It's not a second derivative value. It's a y value. So we're going to plug in the y value, or in this case, the s value. Now we know the endpoints for this x thing are 1 and 100. You're not allowed to have numbers that are smaller than 1, nor are you allowed to have numbers that are larger than 100. That's by direction. It says here the number between 1 and 100. So you ain't going to do a number 103 or 200. It's all going to be between 1 and 100. So we got critical points. One critical point is -1, but -1 is not possible because it is not allowed. We can only go between 1 and 100. We do have 1, so that's listed again. I'll list it again. That's our critical point. And we also have 0. 0 is a critical point. Maybe I'll just make some more space here. It'll be a little easier to explain. So here's my my 1 to 100. Those are my endpoints. I have a critical point, which is at -1. I have a critical point, which is at 0, and I have a critical point, which is at 1. We know that these are impossible because the directions say the number has to be between 1 and 100. So even if those were smaller sums, we're not allowed to use them because the number has to be 1 and 100. It turns out that this critical point of 1 is also an endpoint, which is fine. We don't have to list it twice. I mean, you can list it twice if you want. 1 would be, or I guess this is an endpoint here. Endpoint. And this is the critical point. I don't know how you want to list them. You don't have to write 1 twice if you don't want to. I'm just trying to convey the idea that you list all your endpoints, you list all your critical points, and then you figure out which one is the smallest, and that's the absolute minimum. So if I plug 1 into this equation, remember my equation is x plus 1 over x. So we have 1 plus 1 over 1, which is equal to 2. And when I plug in 100, this is an endpoint over here. When I plug in 100, I get 100 plus 1 over 100, which is 100.01, 100 plus 100th. Well, 1 is the same number here, right? So we get the same value. We get 2 at one endpoint, 2 at the critical point, and 100.01 at the other endpoint. What is the absolute minimum? It's the smallest possible y value. Ding, 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 ding. It's 2. 2 is the smallest possible y value. So the absolute minimum is a y value equal to 2, or we have a sum equal to 2. So then we would say the smallest, the smallest sum is equal to 2. Is that reasonable? Yeah, it's between 1 and 100. Or no, the x value is between 1 and 100. So if x equals 1, we get a very small sum like 2. So nothing weird happening. We don't have like a negative sum or sum of a billion trillion or something like that. No red flags with this answer. So that would be checking for reasonableness, and that would be the answer for the smallest possible sum. All right, so just very briefly reviewing the steps here. Read the problem carefully, try to figure out what the information is, what they're asking for. Write down variables, really write down variables, know what they actually stand for. Write down an equation for what you're trying to maximize or minimize. In this case, we're trying to find the minimum sum. So I wrote down an equation for the sum. That was this one right here. Make sure that your equation only has 2 variables. If not, just simplify it so it has 2 variables. So we simplified it to make sure it had 2 variables. Then you find the critical points by finding the derivative equal to 0, and when the derivative is undefined. Then you list all the critical points and all the endpoints, and you write down the y value for each critical point and the y value for each endpoint. The smallest possible y value is called the absolute min, and the largest possible y value is called the absolute max. That actually gives the answer to part B. If you look at part B, it says find the numbers between 1 and 100 such that the sum of the number and its reciprocal is large as possible. So all the work is done in part A. And we know from this little table here that y equals 100.01 is the absolute max. So I guess we're supposed to say S, not Y, right? So S equals 100.01 is the absolute maximum sum. So absolute minimum, absolute maximum, same process is what I'm trying to get across here. That's what we're going to be doing in section 4.7. So let me start doing a few more examples. Again, I'll ramp up to be a little bit more complicated as we go along, but all of them are going to have the same essential element of identifying the information, identifying the question, writing out the variables, writing out the equation you want to maximize or minimize, make sure to simplify that equation, find the critical points, etc. That's what we're going to be doing in each of these examples. All right, so let me show you some more of these situations. Okay, so I have another problem here with numbers. So we have 2 numbers, each are 10 or larger, and together they add to give a total of 50. What is the smallest possible sum of the squares of those 2 numbers? All right, so this might be a good time to pause since this problem is not too dissimilar from the problem AB that we did before, where we were trying to find the sum of the number and its reciprocal. This is a little bit different, but kind of similar. It's a great time to maybe give it a go. If you want to try, it's okay if you don't finish it. It's okay if you get stuck halfway through, but it's nice to find out. So give it a go. And after you try, unpause the video, and then you can see me talk about how I approach this problem. All right, so here's how I approach. There are numbers, there's two of them. There's two numbers, so I'm gonna have to have a variable for each number. They're both 10 or larger. They add together to give a total of 50. What is the smallest possible sum? So I want the smallest possible sum, that's important, of the squares of the two numbers. So S is equal to the sum, let's say X is equal to one number, and Y is equal to another number, second number. I guess I'll say first number instead of one number, because it sounds kind of funny when I say one number. So first number, we're looking for the smallest sum. So we want the smallest S. To find the smallest S, I have to find an equation for S. So what's my equation for S? So S equals what? Well, it's the sum of the squares of the two numbers. So the first number is X, I have to square that, and I have to add it to the square of the second number, which is Y squared. So that's my sum. I want that as small as possible. It has too many variables, it has three variables, so I'm going to have to reduce the number of variables. I also have to see if there are any endpoints. Okay, so each number is 10 or larger. So I know X is at least as big as 10. Also, Y is at least as big as 10, but I'm going to be reducing this down to one variable anyway. So I'm just going to write this, but you can also write Y is at least as big as 10 if that is something you want to keep track of as well. We also know that the sum, they add together the sum of X and Y, X plus Y, gives a total of exactly 50. By the way, if X is at least as big as 10, then what does Y have to be at least as big? Well, or it can't be bigger than 40, right? Because if it was bigger than 40 and X is at least 10, it wouldn't add up to 50. So we know that Y is less than or equal to 40. And by the way, we also know X is less than, because it's symmetrical, right? If Y is less than or equal to 40, and then X has got to be bigger than 10. But if Y is bigger than 10, then X has got to be less than 40. All right, so with a little bit of reasoning here, we know there are limitations on our X and Y. X has to be at least as big as 10, but it can't be larger than 40. Same thing with Y. Okay, so let's go ahead and see if we can finish this problem up with some critical points, endpoints, things like that. All right, to find our critical points, we're going to have to differentiate this thing, but we cannot differentiate it in its current form because it has three variables. So we need to somehow simplify this. And this is sometimes where people get stuck a little bit, like, how do I simplify this thing? They have to give you information to be able to simplify. It's got to be like a puzzle, right? It's got to be, put your, monocle on, you're a detective. They have to have given you information to simplify this. You just got to sort of, take a deep breath and say, where is the information where I can simplify this into two equations? And the answer is right here. The answer is, that X plus Y is equal to 50. That's information that we know. We know, I'll write it up here, X plus Y is equal to 50. How does this help us? Because I can solve for Y and get rid of it. Y is equal to 50 minus X, and I can take this and I can put it into my equation, and then I'll have reduced the variable Y into 50 minus X, and I'll only have X's at this point. So S is equal to our X squared plus Y squared, but instead of Y, we're going to use 50 minus X. So here's an example of where you can simplify your three variable equation into a two variable equation if you sort of hunt around and use the information they're given to us. We know the X plus Y is 50 because they told us. They together give us a sum of 50. So you just got to make sure to, take a deep breath and know that the information has to be somewhere. All right, so I'm going to differentiate this thing. ds dx. So that's 2x. This is a chain rule problem. 2 times 50 minus x to the first power times the derivative of the inside, which is -1. And I'll just clean this up a little bit just so it's easier to work with. I get 2x. I get 2 times 50 times -1, so that's minus 100. And then I get 2 times minus x times -1, so that's a plus 2x. So my ds dx equation would then be 2x plus 2x is 4x minus 100. I need more space over here. Okay. So that's my derivative equation. And once I have my derivative equation, I can find my critical points, because all I do is take my derivative and set it equal to 0. And I also find out when the derivative is undefined. The derivative is a linear equation. Lines are undefined, so this is a never undefined. So we're kind of good with that. And then this one's simple linear equation to solve. So I get 25 is a critical point. No critical points from when the derivative is undefined, but we do get a critical point when the derivative is equal to 0. So I have my critical point, 25. I also have my endpoint. Remember, 10. X can't be smaller than 10, has to be 10 or bigger, and X can't be larger than 40. So 10 and 40 are my two endpoints, and 25 is my critical point. So now, my friends, all we do is just write them out, and whichever one is the smallest would be called the absolute minimum. So I have my X values and my Y values, which are S values. The S, if I remember correct, is x squared plus 50 minus x squared. We have our two endpoints, 10 and 40. Those are the biggest and smallest x could be. And then we have our critical point, 25 in between. So this is our critical point, this is our endpoint, and this is another endpoint, just to help people see what I'm doing. And then I'm just going to plug it in and find out which is the biggest and smallest for the sum here. So I plug in 10, plug in all these numbers into the formula here. I get 10 squared, and I get 50 minus 10. 50 minus 10 is 40 squared. 40 squared is 1600, so this is 1600 plus 100 is 1700 for that guy. I plug in 25, so I get 25 squared plus 50 minus 25 is 25 squared again. So 25 squared is 625, 625 doubled, 625 and 625 is 1250. And then I'll plug in 40, that would give me 40 squared plus 50 minus 40 is 10. And that's kind of the thing we did before, but backwards, so it's also 1700. And we're looking for the absolute minimum. So the minimum has to occur either at an endpoint and a critical point. We have all the endpoints, all the critical points written out, which is the smallest one. There it is. Right? So we know that the smallest sum of the squares is equal to 1250. And that occurred when x was 25, by the way. So if x equals 25, it gives the smallest possible sum, but the answer is always the y value. The smallest sum is 1250. The smallest sum is not 25. That's just the x value that happens to give the smallest sum. All right, so that's my answer written out to the question. How'd you do? How far did you get? Did you get that answer? There are different ways of doing this problem. So if you did it a slightly different way and got the right answer, probably you did it the right way, the way that works for you. Make sure your method is actually valid and works in all situations. You didn't just get lucky because of the particular circumstances of this problem. So you can always run it by me if you want to know whether your version of the solution works in all situations. All right, like I said, the rest of today is just doing more examples of word problems, trying to make them get a little bit more difficult each time. But that's kind of what we're doing. So feel free to work on these and then check out your solutions or follow along as I explain some of these as well. Okay, well, let me zoom in so I can read this better. I'm going to do example D. It says 1,200 meters of fencing is available to construct an animal pen. It is to be constructed along the side of a barn so that only the other 3 sides need to be fenced. What should the dimensions be in order to create a pen with the largest possible area? Okay, so we have more wordy problems now. We have 1,200 meters of fencing. Let me use non-black here. Let me use green, or let me use blue. So we have 1,200 meters of fencing. That seems to be important. We're making an animal pen. I do believe I was supposed to say a rectangular animal pen, but I don't think I wrote down rectangular. So sorry about that. I forgot that instruction because the shape matters. I should have put in my directions rectangular. So just insert that yourself. It is to be constructed along the side of a barn. So there's a barn. Let me draw a barn here. Here's my barn. No comments on my drawings. All right, there's my barn. On the side of a barn. So here's the side. Here's the side of the barn. It's to be constructed along the side of a barn. So only other 3 sides need to be fenced. So we're making an animal pen where we have a rectangular shape and 3 sides. I don't know, it doesn't have to be the same shape as the barn or same size of the barn. It could be like this, right? So it could be something like that, right? This is our pen. It uses this one side of the barn. So the other 3 sides need to be fenced. So these 3 sides need to be fenced. So this is fence, fence, and fence. So 3 sides need to be fenced. Okay. What should the dimensions in order to create a pen with the largest possible area? So we want the largest area. Okay, so we need some variables. So certainly we need a variable for area. So let's say A equals the area. And this, of course, is of the pen. We're not interested in the area of the barn. We're interested in the area of the animal pen. We need some dimensions here. So let's call the horizontal dimension X and the vertical dimension Y. And because of symmetry, this also has to be X. So X is equal to the horizontal distance and Y is equal to the vertical distance. Okay. And I do believe they're all measured in meters because we talked about meters. So I'll just say in meters. And then area is measured in meters, so in square meters. So that may come up later when we're trying to write out our answer. So I'll just keep track of it now. Okay, so if we're going to try to find the largest possible area, we need an equation for area, right? We can't find the largest area without an equation for area. So we need an equation for area. This is the area of the pen. So this is largest area of the pen. That wasn't clear. Here's my pen. How do I find the area of this pen? Well, it's a rectangle. So the area of a rectangle is length times width, in this case, X times Y. Right? Horizontal times vertical, as long as they're perpendicular, is the area of a rectangle. Okay. So that's my area equation. And it has 3 variables. So let's make sure we reduce the number of variables to 2 so we can effectively differentiate it and find the critical points. So there must be some other piece of information that I have not written down yet that will help me reduce the number of variables down to 2. And I actually have it circled here. If you didn't notice, I said 1,200 meters of fencing. So we have 1,200 meters of fencing, which I never wrote down. So let's write down now. So this is fencing, this is fencing, and this is fencing. There's 3 sides that need to be fenced. So 1,200 has to be the fencing for those 3 sides. So we have X amount of fencing on the top, we have Y amount of fencing on the vertical side over here on the left, and we have X amount of fencing for the bottom. So we know that X plus Y plus X, that distance plus that distance plus that distance, has to be 1,200. All right, and then I can just solve for Y. This is Y is equal to 1,200 minus 2X. And I can take that and I can plug it into there. And that will give me an equation with only two variables. All right. Are there any endpoints on this problem? Well, x is the vertical distance. No, x is the horizontal distance from here to here. So are there any restrictions on x? Well, x is a distance, so we know x has to be not a negative number. In fact, it probably shouldn't be zero either, because you don't really get a fence if you have a size zero, but I'll just include zero in the extreme case, because it could be like 0.00001. I'll just say zero. It's a nice endpoint. So is there a biggest x can be? Well, we know that the total is 1200. So x plus y plus x has to be 1200. So what could the possible biggest of x be, right? This, by the way, is 2x plus y is equal to 1200, if that wasn't clear. So the biggest possible x would be 600. 2 times 600 would be 1200. You can't have bigger than 600, because then it would be bigger than 1200. So x is between 0 and 600. So those are some endpoints. All right. So we have some endpoints. Let's find some critical points, and then we'll find the absolute maximum, the largest possible area. All right, so we have our function here, and we need to find the derivative. We can use the product rule because this is a multiplication, x times 1200 minus 2x. I'm just going to multiply it out because I think it's easy to distribute, and then I don't have to use the product rule anymore. So I get 1200x minus 2x squared. And now the derivative is much easier for me to find. So I get 1200 minus 4x. I have to find that when it's equal to 0 and when it's undefined. So it's never undefined because this is a linear equation. Linear equation, we don't divide by 0. We don't take square roots of negative numbers. We don't take logs of 0 or negatives. None of that stuff comes. It's just a line. So we can solve this equation here. And we get 300. So this is our critical point. All right, and now all I have to do is list our critical points and our endpoints. So we have endpoints. What was our endpoint? Here it is. Endpoints were up here. So 0 and 600 were our endpoints, and 300 is our critical point. And I'll just make little notations here for people to follow along. This was an endpoint. This was an endpoint. And this is a critical point. So we list our critical points or endpoints. And then what do we put these numbers into? What equation? The answer is we're looking for the maximum area. So we got to plug it into the area equation. That will tell me which is the biggest area. So the area equation, I simplified it. So I'll just use the simplified version. 1200 x. Actually, I think the factored version might be easier because I'm not using a calculator. I'm doing it in my mind. If you had like a calculator, I would use the multiplied out version, but I'm going to see if this version is actually easier for me to compute, because I just have to multiply two numbers at the end. So you can use any version of the area you want, as long as you plug in the numbers. So I'm going to plug in 0. If I plug in 0 into this thing, what do I get? I get 0 times 1200 minus 2 times 0, but 0 times anything is 0, so that's definitely 0. If I plug in 300, I get 300 times 1200 minus, well, twice 300 is 600. So I get 300 times, I need some more space here on the right. So this is 300 times 600. 3 times 6 is 18, and I have 4 zeros. So 180,000. That's the value at 300. 600, I plug in 600, so I get 600. And then 1200 minus 2 times 600. 2 times 600, 2 times 600 is 1200. So I get 600 times 0, which is equal to 0. We are looking for the largest possible area. Well, of these possible largest areas, it's got to be this one. This is the only one that's not even 0, right? So the largest possible area is 180,000 square meters. Largest area equals 180,000 square meters. I'm not sure if you felt the same way, that that was a little bit harder than before. But that was sort of the idea, is to show you different kinds of absolute max, absolute min problems, word problems. So that had more words in it. So I imagine for some of you, that probably seemed a little more difficult at first. But what I'm really trying to get across here is that the method is always the same, right? Write down the information, write down the question, write down your variables. If you're trying to find a maximum or minimum of a thing, find an equation for that thing. You cannot find the maximum minimum of any variable unless you find an equation that has that variable in it. So in this case, we're trying to find the maximum area. So I found an equation for area. Make sure your equation has only two variables in it. Oftentimes it will have more than two variables. So just simplify it using the information in the problem so that you only have two variables. Make sure to notate any possible endpoints, find the critical points, list them all out, and you can answer the question. All right, I think we're almost done. I think we have two additional problems here to practice, E and F, and then that's it for my lecture on word problems where we're trying to find the absolute max, absolute min. Okay, so E talks about the length of a rectangle. It needs to have an area of 55 square meters, but no side can have a length, that is longer than 11 meters. We're looking for the smallest possible perimeter of such a rectangle. That is kind of similar to the previous problem. It's not an animal pen, but it's also a rectangle type problem. So that might be a good one for practice. Now that you've done a rectangle type problem with me in the previous example, maybe you can venture and try a rectangle problem on your own. And part F is we have a wire. We are given the task of cutting a 4-foot wire into two pieces with the following goal. The first piece will be made into a circle with radius r, and the second piece will be made into a square with side length s. And the total area of the two shapes should be as small as possible. So I'm going to give you a head start with this problem in case you want to pause the video and give these a try. So we have a 4-foot long wire. So we can make it an axis with starting at 0 and 4. And it's cut into two pieces. So somewhere along this wire, I don't know, let's say here, we're going to cut it, right? So this distance right here would be X. That would be our first piece, would be X distance long. And then the other distance, if this piece is X and the total distance is 4, if you haven't done these kind of problems recently, it may be a little bit confusing as to what this other side was going to be. You can write down y, but you know what this y is equal to. It's equal to 4 minus x. Right? 4 minus x plus x is equal to 4. So if the first part is like, say, 2, the second part also has to be 2. The first part is 1, the other part has to be 3. The two of them have to add up to 4. So whatever 1 is, the other's got to be 4 minus that number. So this first section right here, which has a distance of x, is going to be made into a circle. And the round part here is going around. It's the outside has a length of x. And the second one, the second part here, so that's the first part, is made into a circle. The second part is made into a square. Square means all the sides are equal length. And again, the outside is what we made the wire into the outside. The outside length, in this case, since it came from 4 minus x, the outside length is y, or 4 minus x. So that's a little bit of hint on letter F. So again, my appeal would be to pause and give one or both of these a try. The rectangle one and this weird wire cutting one where we end up with a circle and a square. I'm going to write out my solutions and then I will go over them with you. So I'm not going to go over them live necessarily, but I'll just recap how my approach was. So it would be helpful if you did try them so you can sort of know where the harder parts are and where you can match up with the way I did my solution. Okay, see you in a bit. Okay, so I've written out my solutions and I'll just go over those briefly with you. So for part E, I drew a rectangle. I have the horizontal length as X, the vertical length as Y. I use the variable A for area and the variable P for perimeter. And we are specifically looking for the smallest possible perimeter, p-value. I know the perimeter of this shape is 2x plus 2y, and that has three variables in it. So I need to reduce this down to two variables so I can take the derivative and find the critical points. I do know that the area is 55. That was given to me in the problem description. The area of a rectangle is x times y. So I know x times y is 55, and I can solve for y. It's 55 over x. So I can plug that in there. Instead of y, I have 55 over x. And that gives me this equation right here, this objective equation, as 2x plus 110 over x. That's the equation I need to differentiate to find my critical values. I do have some endpoints. It does tell me that the area is 55 and that the side length can be can the side length can be no longer than 11. So I know that x has to be less than 11, and since they multiply to be 55, I know x has to be at least as big as 5. So 5 and 11 would be my two endpoints because I know x can't be as big as 11, and the two numbers multiply to be 55. Okay, so I have my endpoints, 5 and 11. I'm going to find my critical points. I find my derivative. I set it equals 0 and find out when it's undefined. When I set it equals 0, I found two critical points, one at positive square root 55 and one at negative square root 55. And it is undefined when x equals 0. So there are three critical points, x equals 0, x equals positive root 55, and x equals negative root 55. But I did note that we have a restriction on x. X has to be between 5 and 11. 0 is not between 5 and 11, so I can just throw that away. And negative square root 55 is not between 5 and 11, so I can throw that away. So the only critical point which is possible is positive square root 55. So then I just wrote down those those endpoints and that critical point, and I calculated the perimeter value. We're looking for the smallest possible perimeter. So I calculated the perimeter value for each of those three using technology, and I got 29.665 is the smallest possible perimeter, and that came from plugging in square root 55. So if you want the exact value of the smallest possible perimeter, it would be plugging in square root 55 into this formula, which would be 2 square root 55 plus 110 over square root 55, or as a decimal, approximately 29.665 meters. That would be the smallest possible perimeter of this rectangle thingy thing. And for the second problem, I started off a little bit for you. We have this piece of wire. It's broken off into two chunks. The first chunk we're going to say is x. The second chunk is 4 minus x. That first bit is turned into a circle with radius r, and the second bit is turned into a square with side length s. So I have my variables here. R is the radius of the circle, s is the side length of the square. X is the length of this first piece, y is the length of the second piece, but we know that y is just 4 minus x. We know that the sum is equal to 4, and we know that the second piece has got to be 4 minus x. Since these things add to 4, and because they're physical lengths, I know that they have to have a length at least as 0, can't have a non-negative length. And since it adds up to 4, then the maximum x can be is 4, since we're not allowing negative y values. So we have endpoints of 0 and 4. What are we looking for? Well, we're looking for the smallest possible area. So we need an equation for the area, the total area. So the total area, it'd be the area of the circle and the area of the square. The area of a circle is pi r squared, and the area of a square is s squared. S being the side length, right? Side times side is the area. So too many variables, so we need to reduce them. In this case, we know that the perimeter of the circle is equal to x. That's because the first length of wire had a length of x, and we bent that into a circle. So the outside, with the perimeter or circumference, some people say, has to have a total length of x. But the formula for the perimeter of a circle is 2 pi r. So I know that 2 pi r equal to x. and I can solve for r. R is x over 2 pi. And so I can put that in for my r value. That's how I got x over 2 pi. So instead of r squared, it's x over 2 pi squared. Similarly, we can get an equation involving s. So the second piece of the wire, which was 4 minus x, was bent into a square. So the perimeter of the square has to have a total length of 4 minus x, because that's how much wire we used. So that's this guy right here. Perimeter is 4 minus x, but the perimeter of square is just sides plus side plus side plus side, or 4 times the side is equal to 4 minus x. And I solve for s, which is 4 minus x over 4. And I put that into this equation right here. So instead of s squared, I have 4 minus x over 4 squared. So that is my equation for the area, written in terms of just two variables, x and a. So this is good. Now I can find the derivative and find my critical points. I did clean this up a little bit to make it easier to differentiate. Maybe you didn't. It's really a personal choice. So I just squared things out. I found my derivatives. I have to set my derivative equal to 0, and I have to find out when my derivative is undefined. I noted that this is never undefined because there's no division by 0. Division by 4 pi, that can't be 0. Division by 16, that can't be 0. So there's no division by 0 possible. There's no square roots. There's no logs. There's no tangents. This is never undefined. So I just have to set it equal to 0. I set it equal to 0. I use my algebra skills. So I move things around, and I got a value of x as 32 pi over 32 plus 8 pi. Kind of a crazy value of x. But you can see what I did here. I kind of moved things to either side, and I cleared out the denominators, and then I grouped all the x's on one side, and I divided by the coefficients, and that's how I got my value of x. So that's my only critical point. And then I have over here, I list my endpoints and my critical point. So I know x can't be smaller than 0, and it can't be bigger than 4, right? Because it's the first bit of the wire. So the smallest it could be is 0, and the biggest it could be is 4, because it's a 4-foot long wire. And then I just took those various values of x, the endpoints, and of course the critical point, and I plugged it into my equation for the total area. And when I plugged in 0, I got 1. When I plugged in this 32 pi over 32 plus 8 pi, got about 0.560. And when I plugged in 4, I got about 1.273. I am looking for the smallest total area. So I know it's got to be one of these three things. This is the smallest one, so that's got to be the one that's it. So the smallest possible total area is the 0.56. Approximately, I mean, I could write out the exact answer, but it looks very messy. So it's approximately 0.560 feet. So that's my explanation for the second solution. Zoom out a little bit here in case, I guess I can't zoom in that much. In case you want to take a screenshot of this, it's very small. Sorry about that. Maybe I'll zoom in a little bit, the top and the bottom, in case you want to take screenshots of those separately. But that is it for today's video. Hopefully this was useful and helpful in terms of how to solve word problems that lead to a maximum or minimum value. Maximum, minimum word problems, absolute max, absolute min. All right, well, I hope you have an enjoyable day, and I will be signing off as soon as I zoom in for each of these problems individually for those who want to take screenshots of the problems in a little bit larger typeface.